This video is brought to you by mywayteaching.com.
So in this particular part, we are going to study about the shear modulus, which is so we already studied Young's modulus. Now it is another type of modulus, which is called as shear modulus. See, the ratio of shearing stress to the corresponding shearing strain is called shear modulus of the material, and it is represented by G. Okay, we can write it as the ratio of shearing stress okay, that is given by sigma s to the shearing strain. Okay, shearing strain is nothing but shear modulus. Okay, and we already know shearing stress, that is force per unit area, the restoring force, and shearing strain, the displacement delta x to the original length L. So we can write it as F cross L by A cross delta x, isn't it? Yes. So we know theta is equal to, what is theta? Yes, we can replace this by theta, that is F by A, restoring force, or the shearing strain, we can represent it by theta. So which is given by F by A cross theta, another way of representing it. So the shearing stress can also be represented as, okay, the shearing stress is represented by sigma s, which is equal to the shear modulus multiplied with theta. So the SI unit of this shearing modulus is given by Newton per meter square, or we can represent it using the unit Pascal. The shear moduli of a few common materials, okay, is given in this particular table. See, it can be seen that the shear modulus is generally less than the Young's modulus. For most of the materials, G will be equal to 1 by third of the Young's modulus. Okay, for aluminium it is 25 Newton per meter square. For brass it is 36. For copper it is 42. For glass it is 23. For iron, lead, nickel, steel, tungsten, and wood is having the least. Not lead is having the least of 5.6, and second is wood, and the highest is I think tungsten, which is equal to 150 Newton per meter square. Okay, as per this particular table. Okay, so now let us consider a simple problem. A square lead slab of side 50 centimeter and thickness 10 centimeter is subject to a shearing force on its narrow face of 9 into 10 raised to 4 Newton. So the lower edge is reverted to the floor. How much will the upper edge be displaced? So from the question itself, we are we came to know that they're asking us to find the value of delta x, that is the displacement, isn't it? So you can see this figure before proceeding with the solution. A square lead slab of side 50 centimeter and thickness 10 centimeter is subject to a shearing force. The lower edge is reverted to the floor, you can see here, and the upper edge will move a slight, it will cause a displacement of delta x, and this is theta, isn't it? So the lead slab is fixed and the force is applied to the narrow face. The area of the face parallel to which this force is applied. So the area of the force is given by, since okay, both length as well as width is given, 50 cross 10, 0.5 meter and zero point 0.1 meter, which is given by 0.05 meters square. Okay, so stress applied. Okay, so here they have given the shearing force. So 9.4 into 10 raised to 4 Newton, 0.05 Newton, 0.05 meters square, which is given by 1.8 into 10 raised to 6 Newton per meter square. So we know that the shearing strain, is given by delta x by L, isn't it? So here that is equal to stress from the formula by G. So here we want only the displacement delta x, so we can write it as stress multiplied with L by G. Okay, so we know the value of stress L and G, so we can calculate delta x. 1.8 into 10 raised to 6 Newton per meter square, and 0.5 meter square is the length, and G is 5.6 into 10 raised to 9, which is given by 1.6 into 10 raised to minus 4 meter, or in other words 0.16 mm. Okay, so this is the value. So now let us study what is bulk modulus. So we have already seen that when we submerge a body in the fluid, that body is subjected to a hydraulic stress, isn't it, which is equal in magnitude to the hydraulic pressure. So this leads to the decrease in volume of the body, thus producing a strain which is called as volume strain, and we studied about this, isn't it? Since an equal pressure is applied from all the side, the volume of the body is reduced and it will result in volume strain, which is nothing but change in volume to the original volume. So the ratio of hydraulic stress to the corresponding hydraulic strain is called as bulk modulus. Then this bulk modulus is nothing but the ratio of hydraulic stress to the hydraulic strain. So we call this ratio as bulk modulus. So this bulk modulus is denoted with the symbol that is B, which is equal to the hydraulic stress, and hydraulic strain we already know that is delta V by V, isn't it? The negative sign indicates the fact that within an increase in pressure, a decrease in volume occurs. So that is, if P is positive, then this stress, okay, within an increase in pressure, decrease in volume. If P is positive, then delta V is negative. Thus, for a system in equilibrium, the value of bulk modulus is always positive. So if P is positive, delta V will be negative. So it results in the positive value of bulk modulus. Okay. And the SI unit of this bulk modulus is same as that of pressure, which is nothing but Newton per meter square or Pascal. So the bulk moduli of few common materials is given in this table. See, for aluminium it is 72, brass 61, copper, and liquids like water it is 2.2. For ethanol it is zero point 0.9, carbon disulfide, glycerin, mercury, and for air it is 1 into 10 raised to minus 4 Newton per meter square. Okay. This is the bulk moduli of some common materials. See, the reciprocal of this bulk modulus is nothing but compressibility. We call it as compressibility. Okay, the reciprocal of bulk modulus. It is denoted with K, the symbol K. That is given by 1 by P, the reciprocal of bulk modulus. We already know the equation for bulk modulus. So it can be represented like this: 1 by delta P delta V by V, isn't it? So it can be seen from the data which is given in this particular table. The bulk moduli for solids are much larger than the liquids, isn't it? Which are again much larger than the bulk modulus of gases. So usually the bulk modulus for solids will be larger compared to liquids and gases. Again, if you compare liquids and gases, the bulk modulus of liquids is larger compared to gases. So the solids are least compressible, whereas gases are most compressible. So if you calculate the compressibility, in that case, since it is reciprocal of bulk modulus, for gases that compressibility will be higher compared to liquids and solids. So gases are about 1,000,000 times more compressible than solids, isn't it? So gases have large compressibilities which vary with pressure and temperature, isn't it? Yes, and the incompressibility of the solids is primarily due to the tight coupling between the neighboring atoms. Okay, that is in case of solids, we can see that the molecules in liquids are also bound with their neighbors, but not as strong as we can see in solids. So molecules in gases are very poorly coupled to their neighbors. So in the so in the stress, strain, and various elastic moduli you can see in this particular table. See the type of stress, that is tensile. In that stress, two equal and opposite forces which are perpendicular to opposite faces, that is given by F by A. And elongation is strain. Change in shape or volume, change in shape it is yes, but change in volume no. And elastic modulus or Young's modulus Y is given by F cross L by A cross delta L, and name of the modulus is Young's modulus, and state of matter is solid. Similarly, in case of shearing, hydraulic, we can see here in shearing, two equal and opposite forces parallel to opposite surfaces. Again, it is given by F by A, and that is strain is theta, and shape change yes, but volume no, and G is given by F cross theta by A, and shear modulus, the state of matter is solid. In case of hydraulic, forces perpendicular everywhere to the surface, and that is force per unit area is same everywhere. And volume change and shape no, it will not change, but volume change will takes place in case of hydraulic stress. And that is bulk modulus, that is given by minus P by delta V by V. And the state of matter, it can be solid, liquid, as well as gas, isn't it? Yes.